In this video, I'm going to be going through Unit 2 worksheet, so let's jump right in. Number 1 says, describe the structure or the parts of an atom and rank them most to least according to how much mass each contains and how much space each takes up. So if we describe the structure of an atom, what we're doing is assigning a location for each of these subatomic particles. There's the neutron, there's the proton, and the electron. We can abbreviate these as such. This indicates their charge. Neutrons have no charge, protons have positive charge, and electrons have a negative charge. These two are going to exist inside of the nucleus. And the electron will exist somewhere on the outside of the nucleus. As far as which one is the most massive, that is the neutron. The neutron has the largest mass, although it has just a small bit more mass than a proton. The electron is much, much smaller than both the neutron and the proton. And so as far as which one takes up most space, that's actually going to be the electron. So if I was to draw this truly relative to scale, and I'll kind of approximate it here, the nucleus would be somewhere right here. And again, this isn't going to be exactly to scale at all, but bear with me. Nucleus is down here. The electrons are way out here somewhere. And this is nowhere close to at scale. But suffice it to say, the electron cloud takes up much more space than the nucleus. The nucleus is the most massive part of the atom, so it contains the most mass, but the least amount of space. The electron clouds are least massive, but contain, or take up rather, the most space. If you remember the analogy from class, the nucleus is the beach ball or the football at the middle of the stadium, and the electron cloud is the remaining stadium. So the electron cloud takes up much, much more space. Okay. The next couple are items that come from looking at the periodic table. So this is just really going through the symbols and the names. AU is the symbol for gold. Silver has a symbol AG. Cr is chromium. Potassium symbol is K. Cadmium has the symbol CD. Platinum has the symbol PT. Na is the symbol for sodium. And magnesium has the symbol Mg. Again, you would just have to memorize those, but you can find all that information on a periodic table that has the names and symbols on it. All right, the next one is filling in a table. And this table has to do with the number of protons, the symbol that we would use, the neutrons, and the total number of electrons, and then finally the mass number. So I'm going to draw over here just a generic X. There's no atomic element with the symbol X, so it's just a generic placeholder. But here at the bottom would be the number of protons. That's where you would find that. At the top would be the mass number. And then if there was a charge, that would exist over here on the top right. The proton number tells us the identity of the element. So you can either look at the symbol or you can look at the proton number to determine what the element is. In this case, I have the symbol AU, and if I go to the periodic table and look up the atomic number, or the number of protons for AU, I see that it's 79. It's element 79. If I want to find the number of neutrons, I take the mass number and I subtract 79 from the mass number. And if I do that, I should get 118 for the number of neutrons. And then the total number of electrons is always going to be equal to the number of protons if there is no charge. Since there's no charge here, that means that the protons and electron numbers total, we'll talk about something called valence electrons later, but right now this is total, is going to be equal. Then the mass number I find by looking up here. For this particular atom, the mass number is 197. I want to make clear that you don't find the mass number by looking at the periodic table. The periodic table gives you the average mass for all of the isotopes of that element. Here I have one specific isotope, gold, now 197, so I need to attach a mass number for gold 197 that is specific to that isotope, and that of course is the number 197. Alright, up here I don't have a symbol, but I do have the number of protons, which can tell me what the symbol is. If I go to the periodic table and look at element 56, I see that that element is barium. And I'll put the mass number up here when I've calculated that. So barium is element 56, which means it has 56 protons. This particular isotope of barium has 82 neutrons. So if I want to know the mass number, I would add 82 plus 56, which is going to be 138. So I can put that 138 up here. So this isotope is barium 138. Remember that the total number of electrons is going to be the same as the protons if there's no charge. So that will be 56. Here again I have the number of protons but no symbol, but I can very easily look and see that element 15 is phosphorus. I don't have the number of neutrons here, but I do have the mass number. So if I want to find the number of neutrons, I just take 31 minus 15, the number of protons, and I get 16 neutrons. Remember that the mass number is a composition of protons plus neutrons. So I can put 16 up here. Or, excuse me, that would be 31. All right, that's it for number 3. Let's turn the page here and move on to nuclear radiation. Whoops, skipping ahead. Number 4, atomic size. Question asks us to arrange the following items in terms of increasing atomic size. So that's small to large. I'm going to zoom the camera out a little bit and bring out my periodic table here. I know there's kind of a glare. Try to get rid of that. But if we look at the periodic table, remember that atomic size increases as we move to the left and down. So francium, way down here, and cesium, these are the two largest elements. They take up the most space. Whereas up here at the top right corner, fluorine, well, really helium, helium and fluorine, these are the smallest elements. Okay, hydrogen also is kind of over here. It's sort of out of place in a way. It's not a metal, but it's way up here. The people who organized the periodic table just figured this is the best spot for hydrogen. So hydrogen is also quite small. Hydrogen, helium, and fluorine, very small. So this one kind of defies the trend a little bit. So be aware of that. But I'm not asked about hydrogen in this problem. I am asked to rank xenon, helium, oxygen, carbon, indium, and cesium and francium, or fluorine. So I know the largest is going to be cesium. Okay, because cesium is way down here at the bottom. So I'm going to go ahead and put cesium over here on the right-hand side. If I look at some other ones here, indium is... where is that one? Here we go. Right here. Okay, element 49. Need to find xenon. Xenon's over here. Helium, of course, is way up here. Oxygen and carbon are up here. And fluorine. So if we're following the trend that down and to the left is larger, then indium would be the next one from cesium. And I'm kind of going backwards here. Following that, xenon is to the right of indium, so it will be smaller than indium. And then moving up to these three, carbon, oxygen, fluorine. Carbon is to the left of oxygen, which is to the left of fluorine. So fluorine is going to be the smallest, or I'm sorry, helium is left there too. Helium is smaller than fluorine. So helium, then fluorine, then oxygen, then carbon. So starting at the top right, we go helium, fluorine, oxygen, carbon, xenon, indium, and then way over here, cesium is the largest. All right, number 5. Five says, draw out the Lewis structures for the following ions. Okay. So again, you're going to need your periodic table for this one, but I'm going to just do it without the periodic table because I know what these are. Starting with cesium. Cesium is in group 1, which means it's at the very bottom. We just saw it. It has one valence electron. Remember, with Lewis structures, we're dealing with valence electrons, those outer shell electrons, not with total electrons. So we just have one because it's in group 1. Bromide. This is bromide because it is an ion. Bromine has 7. But since we have a 1 minus charge on this bromine, we call it bromide. And it has 1 additional electron. So this bromide ion has 8. So it has an octet. K normally would have 1, but because there's a positive charge, it's just like cesium, it's in group 1. There's a positive charge, we remove that 1 electron, so K actually has no valence electrons here, because we've removed its 1 valence electron. S is in group 6A, so it has 6. It's in the same group as oxygen. So we will have 6 valence electrons. Nitride has 8. Nitrogen has 5, and then we add 3 additional electrons to make it 8. Magnesium would normally have 2, but because there's a 1 plus charge, we're going to remove 1 of those 2, leaving magnesium with just 1 electron, 1 valence electron. All right, number 6. Identify the particle array involved in each and what the charge is. Which is most dangerous if the radiation source is external, which is most dangerous if the radiation source is inside the body, and explain why for both. Okay. So let's go ahead and just put the symbols here. For alpha, here's the symbol. Sometimes it's also denoted like this. Okay, but there's the alpha part. We call this a helium nucleus. They're the same thing. The charge on this is going to be 2+, because it has 2 protons. In beta emission, here's the beta particle, sometimes also denoted this way as an electron, same thing, and the charge here is going to be -1. For a gamma ray, I'll just draw this over here. For gamma rays have no mass and they have no charge. Gamma rays are part of electromagnetic radiation, part of the electromagnetic spectrum. So they are essentially light rays containing no mass or no charge. And then the final one is a positron. Positron looks very similar to a beta particle, except it has a +1 charge instead of a -1 charge. As far as which one is most dangerous if the radiation source is external, that is going to be gamma rays. The reason is none of these can penetrate the skin, or at least not to a very deep level. Beta emission can sort of penetrate the skin, just slightly, but not much. However, gamma rays can go right through you. So gamma rays can go through you, and on their way through you can slam into all sorts of things, causing damage. So gamma rays are the most dangerous for external. For internal, alpha particles are the most dangerous. The reason being that once they're inside of you, they don't need to get through your body at that point. They're already inside your body and can cause tremendous amount of damage because they're so large. The size of this and the momentum that it carries is much, much larger than either beta or gamma. So it's like a freight train slamming into your cells. Okay. Last problem. Number 7, half-life. Question A says, how long is the half-life of americium 214 of 6 grams of the original 96 grams sample remains after 866 years? First thing we need to figure out is how many half-lives have passed. In order to do that, I'll start with what was originally there, the 96 grams, and just divide it in 2. Count the half-lives. So 96 grams divided by 2 is going to be 48 grams. Next half-life is going to bring it down to 24 grams. Then 12 grams. Finally to 6 grams. Okay, so there has been 4 half-lives, 4 divisions of this original 96 gram sample. And if we take the 866 and divide by 4, so if we take the total years and divide that by number of half-lives, we will get the length of half-life. So that in this case is going to be 866 years divided by 4, which gives me 216.5 years. So that means it takes 216.5 years for half of the sample to decay. So we could fill this in 216 years, 216 years. Each of these arrows represents 216.5 years. All right. B, a little bit different question. How much of a 30-gram sample of radon-222 will remain after 8 days? Okay, so our original sample is 30 grams. If we know already the half-life is 4 days, we can take the total time, 8 days, divided by the half-life, 4 days, and we get 2 half-lives. Okay? Up here, we were kind of working this problem backwards. So we know this thing has divided twice in the 8 days. So we just draw 2 arrows and divide by 2. So first half-life is first 4 days, goes from 30 to 15 grams. And in the second 4 days, the sample is reduced down to 7.5 grams. Each arrow represents a half-life, 4 days. All right, problem C. 197 mercury is used in brain scans. What percent of it would remain radioactive after 3 half-lives? All right, so this one's kind of missing some numbers, or what you think should be there, but you have to consider that what percent of it would remain after radioactive after 3 half-lives. This implies that we start with 100%. Because if you start with a sample, it is, of course, 100% of itself. Whether it's 1 gram, 10 grams, 100 grams, the starting point is 100%. After the first half-life, 50% will remain. After the second half-life, 25% will remain. And then after the third half-life, 12.5% will remain. We don't need to know how long the half-life is to determine the percentage. We also don't need to know how much we started with, because we know it was 100% of something. And so whatever is left over is 12.5% of what we started with. All right, that's the end of this video. I hope that was helpful.